Hi everyone, today we'll be talking about our work on stream processing with dependency-guided synchronization. This is work that was done with Caleb Stanford, Philip Nixits, and Rajiv Allur at Penn. So before we get started, I will give a summary of the things that I'll be talking throughout in this talk and of what we did in the paper. So in this paper, we propose a new parallel programming model for stream processing applications that is called dependency-guided synchronization. We propose an intermediate representation capturing stateful parallelism with synchronization called synchronization plans. And we also propose a compiler that generates provably correct synchronization plans from these DGS programs. We also propose and implement a prototype that ties everything together. In the paper, everything comes together with an end-to-end proof of correctness. The key insight behind all of this work is that we view streams as partial orders, but there will be more on that later. So let's start with some background on stream processing first of all to understand where all of this comes from. So what is stream processing and why we should all care about it? So stream processing is a computing paradigm where we process input items incrementally. So as they arrive, we process them. And we produce output on the fly without retracting it. The stream processing has some differences, core differences with batch data processing, and these are that the input order matters for the computation. For example, a computation might perform interpolation on the items of the input stream. The input is often too large to be stored and processed later, so it has to be processed on the fly. And finally, output items need to be produced with low latency, so the system needs to be responsive and respond directly when it gets input. So stream processing started from a database community with variants of SQL for streaming, such as SQL. But nowadays, it's most often associated with stream processing systems like Flink, Storm, Kafka, and Timely, which is materialized the company behind it. And there's also continuous interest from academia. For example, these are some recent papers that were published in top-tier conferences on stream processing. The reason why that is, of all this interest, is that there are a lot of applications that fit in this stream processing paradigm. So, first of all, we have machine learning. So, mostly until now, machine learning has been done with batch processing techniques, and we assume that all of the data is already on the disk. But real data is often streaming. For example, when we have users interacting with web services, data arrives in a streaming fashion. And this means that there are a lot of machine learning applications that fit into this stream processing paradigm. Second, we have the domain of Internet of Things, where we have sensors which are used to monitor and perform and manage several things like smart cities or smart houses or warehouses and so on. And all of these sensors, the data coming from these sensors is streaming, arriving as it happens. And we also have finance as a domain, where stock trading, stock prices change often, and so yes, it changes often, and there is need for very quick and responsive outputs from a system. And the common thing between all of these applications is that there is a lot of large input that arrives continuously, and there is heavy need for fast responses. More generally, streaming is the right fit for any event processing. For example, we are recently seeing the emergence of microservice applications, and microservice applications can be thought of as stream processing applications where requests are the input items in your streaming application. So until now, I have hopefully convinced that stream processing is important, and there are a lot of applications and interest on it. But where's the parallelism? Why am I even talking to you at people without any parallelism? So there is actually, as we said, massive amounts of continuous input data that must be processed on time in stream processing systems. And so sequential processing performance is actually inadequate. If we have a lot of sequential load, our system is going to get on fire if it cannot handle this load. And we don't want that, do we? So we need parallelism now. And existing frameworks do support parallelism, and that is actually part of why they have become so successful. but this is in restricted forms. And it's a good question to ask why. So let's go into this a little bit, dive a little bit deeper and see what are the views of streaming and why they inhibit parallelism, or they restrict it in a sense. So the reason is simple, actually, that streams are sequences, and sequences are an inherently non-parallel object. Events usually arrive in the system in some order, and it is natural processing them in this order. For example, if we process first the first event, then the second, and then the third. Existing systems, in order to achieve parallelization, they have to bolt on limited parallelization on top of this sequence model. This parallelization is often called sharding, which is, in a sense, here is an illustration of it. So we essentially partition the input events into different partitions, and we send each partition to a different parallel node. And this is actually very, very, very good for many cases. And this is what existing systems are based on. These cases are, for example, when we have commutativity of our processing and statelessness, then we can simply arbitrarily partition our input events and send them in arbitrary parallel processes. Or similarly, if we know that our computation is stateful, but it is independent, there is independent by keys of the input stream, then we can separate and partition the keys based the input items based on that key and send each key to a different parallel process. But the problem with sharding is that it does not allow for synchronization between parallel nodes. And to understand why this synchronization is important, let's look at an example. So assume that we have a machine learning fraud detection application where the input is bank transaction events, and our goal is to detect the transactions that are fraudulent using an unsupervised online machine learning model. The model is updated every time we process a transaction. So as an illustration, let's say that we get a transaction and then the processing returns that it's a fraud, or similarly, the processor can return that it's not a fraud. And we can keep going, and whenever we process each of these transactions, we update our model, which is the state of the stream processing application. So if we just use plain sharding, there is not any way to communicate between these nodes. So there's no way for these nodes to access the other node's state or update it. And this leads to the following problem, that we either have to use a sequential solution where a single node has all the state, and as we saw before, this leads to fires, and we do not want that. Or alternatively, we can use an ad hoc external state like a key value service with strong consistency guarantees that then in our application code, we can contact and use it to synchronize. However, the problem with this is that existing systems then do not know anything about the state, and this messes up with both parallelization and their fault tolerance guarantees. So there's another field and there's another view on streams, and this is coming from the database community, where they have approached streaming from a different angle, modeling streams as multisets. And this is inspired by all the work on SQL and relational databases. And when we view streams as multisets, the benefit is that they can be processed in parallel, but their stream order is completely lost. And this means that it's very hard to implement order-dependent computation. For example, interpolating on the events of a stream becomes very hard. And so we have seen that there are two opposing but not ideal views on streaming. So the first view is that streams are sequences, and there is limited parallelism, but we can preserve the order and easily make order-dependent computations. And there's the other view that streams are multisets, where there is great parallelism, but the order is lost. So the question is, why don't we just have both? And that's actually the key insight behind our work. Streams are actually partial orders. Who would have thought? Actually, you thought about it because I told you in the introduction of this talk. But yes, the point is that for some events in a stream, the order is important, and they can be processed in sequence. For example, for the events, for the first three events in this graph, the first and the second, they need to be processed in order. while the rest can be parallelized. All of the events that do not have edges between them can be processed in parallel. So this partial order exposes natural parallelization, and as I said, this is the key insight behind our work. So implementing or exposing this partial order when programming and programming on these partial orders is actually challenging, though. For example, in the programming model layer, there's a question of how does the user expose the partial order in their code, or the fact that partial orders are inherently non-deterministic and programming using them, because different unordered events can be processed and arrive in the system in different orders, and therefore there is inherent non-determinism there. But we would like our model to be deterministic. Also, the model needs to be abstract, not mentioning low-level parallelization like the number of parallel machines or the partitions of keys, but also needs to be expressive to capture the fine-grained synchronization that we require, for example, for this machine learning fraud detection application that we saw. And there are also challenges in the implementation layer. For example, how is the partial order-based stream processing implemented correctly, and also can it be implemented efficiently? And to answer all of these questions and to address these challenges with our work on dependency-guided synchronization. So our work, as I said in the beginning, we propose, first of all, a programming model that is called dependency-guided synchronization. And this programming model captures the partial order nature of the input streams. And is high level in the sense that users describe how, but not when, synchronization happens. At the same time, we propose an intermediate representation called synchronization plans. The synchronization plans look like trees, and that's why we have this cute tree logo here. And these synchronization plans are concrete parallel implementations of the DGS program, where the number of parallel workers and the partitions of keys are concretized. And we also propose a compiler that goes between, given a DGS program, produces a synchronization plan. And an important property of our compiler is that its correctness is decoupled from optimality. And essentially, we know that our compiler produces a correct synchronization plan, and then optimality is left to a different optimizing component to deal with. We tie everything together, as I said, with a prototype implementation. Yes, so let's now dive deep into the components of our work and start from the programming model. So how does one capture the input stream partial order? To understand that, let's look at an example, and let's look at a simple application on the machine learning fraud detection that I told you in the beginning. Let's look at an application that implements a map from keys to counters. And let's assume that we have two types of events: an increment key that increments a key for the counter for a specific key, and then a read reset key that outputs the value of a counter for a specific key and resets it to 0. So the state of this application is this map from keys to counters itself. So let's look at how we would write this program in our programming model. So first, let's start with some type definitions where the keys are simple integers. Events are either the increment or the read reset events with a key. The state is a map from keys to integers. And then there's this predicate, which we will use later, but is simply a function from events to booleans. And the first component of an application in DGS is a sequential update function. This sequential update function describes how a single node processes incoming events by updating its state and outputting events. So it first gets an input state and an input event, initial state and input event, and then describes how to produce the next state. So if we get the increment event, then the application simply finds that key in the state and increments it, and then returns the new state. Similarly, if it gets the read reset event, then it outputs the value of the counter and resets to 0. The important thing to note is that these two are actually adequate to get a sequential stream processing implementation. And not only that, but they also act as the specification of our application. So the sequential implementation of our stream processing application is the specification, and we want any parallel implementation that our system produces to be correct with respect to that. So now we saw the sequential code. Let's look at where parallelization happens. I'll keep the type definitions on the side so that we can keep them in track. And so the next component is actually dependencies. So as you can see here, we describe dependencies between input events as follows. We simply, for this example, read reset events depend on read reset events if their keys are the same. Read reset events depend on increment events if their keys are the same and symmetrically. And increment events do not depend on any other increment events. And these dependencies actually give rise to the input partial order. By the way, there's another way of visualizing them more clearly, not with code. So here, as you see, there's a graph. We can visualize dependencies as a graph where dependent events have an edge and non-dependent events do not have an edge. So as you can see, increment events do not have any edge connecting them with other increment events. And as I said, these dependencies give rise to an input partial order. So dependent events are ordered in input and independent events are not ordered. So now that we saw that, let's look at the final component. So until now I have shown you how to derive the input partial order, but now we need the final thing, how to do the parallelization. And so forks, this we do with forks and joins. And forks and joins, essentially, forks describe how to fork a single state to multiple states that can process sequentially with this update input events in parallel. For this example, the fork takes fork takes a single state, two predicates or partitions on input events, and produces two output states. And for this case, it creates two states from the initial state by checking if the key is in the first partition, then it puts that key in the first state, or if it's in the second partition, it puts it in the second state. Join, conversely, takes two of these forked states and merges their dictionaries, these maps together. And these two generated states that fork produces can actually process input items in parallel, as we said. And as I also said, the predicate 1 and predicate 2 are partitions of input events, and the fork needs to be defined on any two partitions that contain independent but not necessarily disjoint input items. For example, increment for 1 could exist in both of these partitions, and our fork needs to handle this. So given that, as I said, an important property of our model is determinism. And so, as I said, partial orders are inherently not deterministic because some events may be processed in different orders. But our programming model ensures that if the program satisfies three consistency conditions, then it is deterministic. And these consistency conditions are these simple conditions that I show here. First, that updates and joins can commute. Then that a fork followed by a join is the identity. And finally, that updates of independent events can commute. And given these three conditions, we prove in the paper that if a program satisfies those, then any execution of it is deterministic and equivalent to a sequential execution using only the updates of this application. So now let's switch gears and start talking about synchronization plans, which is the intermediate representation that we use for concrete parallel implementations. So forks and joins describe how to synchronize, but not when. And also, they do not describe how events are partitioned among the parallel nodes. And this is actually done with synchronization plans. Synchronization plans are tree structures that describe parallel stream processing implementations in our setting. And let's look at an example to understand them better. So an example synchronization plan for the counter program that we saw before, the map from keys to counters, is the following. So we have nodes, first of all. Nodes are workers, and they are parallel processing workers that process input events. And edges represent communication channels between these workers. As you can see, each worker is associated with a set of events that this node is responsible for, or a partition of the events that this node is responsible for. And as you can see, two nodes can have non-disjoint partitions that they're responsible for, as long as they're independent. And as the system runs, what is happening is that when an event arrives, it is routed to a node that can handle it. Then the node runs join on its children state, if it has children. It then runs the update, and then runs the fork. And this means that the leaf nodes process fast without waiting for anything else, whereas parent nodes synchronize and make sure that the state is synchronized across the whole application when order and dependencies exist. And cyclic processes are completely independent and do not know anything about each other. So now let's briefly discuss in the paper we also formally define when a synchronization plan is valid with respect to a DGS program, and you can look for these details in our paper. So let's now switch gears again and talk about the compiler briefly. So our compiler, as I said, generates a synchronization plan from a DGS program, and the correctness, as I said, is decoupled from performance. And what does this mean? That a DGS program provably derives a set of valid synchronization plans, and then a separate optimizing component can search in this set and produce an efficient implementation only as long as it stays in this set. And in our implementation, we have implemented an optimizer that tries to collocate computation with the input, but one could define develop different optimizers that optimize for different criteria as long as they search in this set of valid synchronization plans. And choose a different performance metric to optimize for. In the paper, we have a pen and paper proof that any implementation produced by a framework is correct with respect to the sequential DGS program that the user wrote. And so now I will also briefly give you a hint of what we have in our paper's evaluation. We have several things. First of all, we show that state-of-the-art streaming systems like Flink and Timely have limited scalability in stateful applications that require synchronization. We also show how fine-grained synchronization using synchronization plans can improve scalability of Flink, where we implement a synchronization plan like on Flink, and we show that it can achieve higher throughput than the Flink implementation. We also implement and show the scalability of our prototype implementation, which scales well with respect to the parallel load. And we also show have two case studies to show the programmability of DGS. In these case studies, we show and we see that the effort to write the parallel part of the program is low compared to the sequential one, which we would already have to do to write our program. And so this actually concludes my talk, but briefly let's go into some discussion before ending it. So first of all, we saw that stream processing is an increasingly important computing paradigm, and unfortunately the reason for it is still ad hoc. It is successful, and a lot of existing systems are successful, but it's not expressive enough. And viewing streams as partial orders can enable these parallels that we were missing. And in our work, we propose DGS, a programming model that captures this input parcel order while guaranteeing determinism and also being high level. We also propose synchronization plans that describe finer grained synchronization. And we also propose a compiler that compiles DGS synchronization plans, and its correctness is provable and decoupled from performance.